and try to take you to some of the challenges and some of the excitement of high performance computing. Philosophically, as you know, science began with sort of inquiry, with certain conceptual, certain observations, certain mathematical explorations, what we call theory or models. But then, with the advent of high performance computing, this has emerged as a third pillar of scientific inquiry, because questions that could not be earlier addressed, let alone answered, now can be addressed and answered using high performance computing. So it is indeed a third pillar. If you look back into the earlier certain theories and treatises, it would be some sort of perturbation analysis, linearize the equations, and then try to get some solutions, which could never really be translated to something that is actually applied, because you have to make a lot of assumptions. The advent of computing meant that you can do away with those assumptions. You can actually solve the problem or the system as it is and try to get an applicable solution. So roughly, therefore, we are talking about, when we talk about high performance computing, we are talking about these are that require much larger than a single computer, a computer cluster, and takes much smaller time, because you can then actually apply them. Large input output, and of course large data, which in fact has become another paradigm itself, what is called the fourth paradigm, or the big data science. So these are therefore some of the tasks involved in the measuring applications. You can say that when you have very large scale simulation. Now, what is large scale simulation itself keeps changing, because at some point what was done with a high performance computing now can be done with a PC. What was done with a desktop can be done with a laptop, and so on and so forth. So therefore, it keeps changing. But roughly, you can say these are some of the characteristics or major applications. And these are somehow, you can say, organized high performance computing applications. You have predictive modeling, that means you are trying to say what is going to happen in the future, what is going to happen as a consequence, which is also kind of prediction. You need also analysis, search and compare data, very large amount of data. We are talking about, if you know about the Intergovernmental Panel on Climate Change, they carry out these simulations. In 2013, the fifth assessment report was completed, and the data coming in the first phase was 1300 terabytes. So it's a kind of data we are talking about. So it is very difficult to quickly process them and get information. So you need high performance computing for that. And in fact, in any science area, any engineering area or engineering you can talk about, this now requires high performance computing to get the edge, to get understanding that would not have been possible otherwise. So, which of course, I think Professor Das may be talking more about this, but of course the applications in engineering and manufacturing are clearly understood. And the structure today that is emerging is that you have a petascale supercomputers, and you have then also petascale libraries. Remember that the computer by itself is of no use. You must have those libraries, application software sitting on that, and then depending upon what you want to do, you can put them together and you can address your question. I'll come to this a little bit more in a while. So once again, if you want to make it more specific, you can say climate modeling, simulation and projection. Climate modeling and weather forecasting remain one of the most demanding user of high performance computing even today. But you can also have like drug design and discovery, molecular modeling. You want to design a molecule with specific properties. Ocean exploration, where you are talking about simulating at maybe a few meter resolution. You can imagine space exploration, astrophysics, nanosciences, and as I say, everything else. So in very specifically, now let us say what we are talking about kind of thing, and why, where do we need to go with high performance computing. If you want to say what is the wish list, for example, weather forecasting, the user would actually like to know on demand, I want my forecast at this point now, what is going to happen to the temperature or wind 2 hours from now. We are far, far away from it. We are nowhere near it. Well, on one hand, you can say we can always make a forecast, right? We can do whatever user is asking. Only question is that how good is it? Well, a good forecast at that scale is simply not available today. You also want to project backward, what they call hindcast. What happened 1,000 years ago? What happened maybe a millennia ago? Why was the ice age initiated? How was it initiated? How it progressed? And you also want to simulate forward in time. What is going to happen 10 years from now, and 50 years from now, 100 years from now? So those, as you try to do, you have to ask, are those reliable? Because if you are going to use them simply as a kind of interesting thing, it's one thing. But if you want to use them for policy decisions based on which certain activities will be taken up, then you have to have high reliability, 90%. But we say no false positive, no false negatives. You have to have different ranges of forecast, maybe from hours, decades, and so on. And special coverage has to be station, global, and beyond. We are now talking about space weather. We would like to know how our satellites may be affected by fluctuations in the space weather, and slowly we will be increasing the envelope of our forecast. So there are lots of applications where these such forecasts are useful, and it can save time, money, and all that. And for that, you need to be able to. So this is something where physics and computing they come together. Now you can have, for example, a resolution where a box, a grid, as they call it, the unit box covers all of the both land and ocean, and in the other case it covers only land. Obviously, in the first case, your results will be wrong because where evaporation should not take place, it is only land. Evaporation is taking place because of your bad resolution. In the other case, it is better, so you get a clearer thing. So you see, physics and numerics they couple, and therefore have to be appropriately addressed. So there are other techniques that have to be brought in. This is an example of what you may call a variable grid. You do not want to, you cannot afford same resolution all over the globe, so you focus on a particular area with very fine grid, and then go to the other area with a coarser grid. The point is that these are all technological resource limitations. We are doing this only because we do not have today a computer or a system that can support very high resolution all over the globe. Which means as the technology evolves, you will be able to address those questions more and more. But even now, you can see that it allows you, high performance computing allows you to get insight into phenomena which you could not do earlier. This is, for example, simulation of a tropical cyclone in the Bay of Bengal. The blue and purple dot is the actual one, and the other one is what has been predicted. So you can see that it is much closer to what at one time. There was a time this simulating the cloud cover over the tropics was a big achievement. So those days are gone, and we are now talking about much. But here is an example where you can gain insight from high performance computing that you cannot get otherwise. This is a cyclone that hit the coast of Orissa in 1999. The prediction was that it was going to go and hit Pakistan coast. So what happened? Why it has gone to Orissa instead, and you can see that there was a kind of mechanism which you can see one cyclone, another cyclone evolved during the time, and they took the original cyclone to the coast of Orissa. You can see that here is a cyclone that is most likely go to the coast of moving towards Pakistan, but then another cyclone comes, eats it, and takes it away to the coast of Orissa. These are kind of insights you could not have got earlier otherwise without the high performance computing. So there are many examples, and but then we have to address what kind of computing we are talking about. You need very long runs, as I said, where only parallel computing is can help you, but you may also have very short runs where different kind of computing is applicable. You can also use this to model disease. For example, what will happen if there is a 2-degree warming let us say in Arunachal Pradesh, and it basically shows how some areas will become more vulnerable to malaria than the other areas. And of course, there is always the task of validation. As I said, which a model, which a program, it will always give you some graphics. The question is how to build it, and that is where your validation comes in. And of course, your credentials, so you have to keep up with publications and so on. In Karnataka, we took up with their request. The question was that can we give forecast at Hubli level? Hubli level is a small cluster of village which is still not done in the world. So we took up that challenge, and it turned out that there is some skill, and they did some assessment. It said that every time they use this, something like several 175 crores were saved for the farmers. So just to quickly look ahead, I hope I don't know how many minutes I have. I think maybe 2-3 minutes probably left. So what is coming up now? Where do we fit in? Where do we challenge life? What is coming up? The concept of a problem-solving advantage with high-performance computing. So this will be now where we take extensive use of the web. You have various applications available, prefabricated components available in the web. And something like an object-oriented approach allows you to put this software together so that you can have what you want to ask, somewhat like somewhat like Adam, what it was designed. But it will formulate hypotheses, it will design and run the experiments, it will analyze your data, and it will even tell you what experiments will be done next. So that all it will be. And in 2014, the robot was launched, which is a worldwide web for the robots, or machines in fact. And so, how it will look like is which enable R&D in very near future is that you will have an HPC modeling and data infrastructure at the center, and then you will have various application softwares, whether it is computational chemistry or bioinformatics, material science, we will hear about it, and so on, and of course computer science itself, and all of them, they will work together in this platform to give you completely new insights into this. Cloud computing, of course, and there is of course a big challenge coming up in data storage and amount of data. So it is estimated that 2020 will be about 44 zettabytes of data annually, and it's a conservative estimates. So therefore, we will have to worry about that. You have heard in the morning about quantum computing, of course, which is also in the horizon. So basically, we are talking about, I think, a universe. We're talking about a world which will be mostly, anchored on high-performance computing. Most of the experiments, design, even analysis, even interpretation will be done by these automated machines. So it's a question of whether we can keep up with that and how do we contribute it. I think I'll stop with that. Thank you.